All right, let's look at running through some example calculations here. So let's say we have an aerosol can and it has a gas pressure of 1.5 atmospheres when we're at 25 degrees Celsius. So if we heat this can up to 465 degrees Celsius, what's going to happen to the pressure? What's the new pressure going to be? All right, and keep in mind this is about half the temperature of a typical incinerator where we take garbage and they throw it into a big burner. So keep in mind, whenever you're looking at these problems, think about what's being held constant. All right, be thinking about that PV equals nRT. What components of that are held constant? So in this case, is pressure being held constant? Well, no, pressure is definitely changing because we're wanting to calculate the new pressure. All right, what about volume? Well, volume's being held constant. It's a fixed volume because it's inside that aerosol can. Okay, so we're not changing the volume of the gas. All right, next is number of moles. Number of moles changing? No, we have a fixed number of moles inside that can. We're not letting any out. We're not adding any, so it's a fixed number of moles. What about temperature? Temperature is definitely changing. So let's derive our equation we want to use. Set everything that's constant on one side of the equation, everything that's changing on the other. And we get our P1 over T1 equals P2 over T2. Well, then it's just a matter of plugging those values in, right, and making sure that we're in the appropriate units. Remember, we need atmospheres, liters, moles, and Kelvin are the appropriate units. And then solving for the new pressure. So the new pressure inside the can would be 3.7 atmospheres. Okay, now that's only halfway to the temperature what an incinerator would get to. But with that much pressure inside the can, what do you think is going to happen to the can? Well, the can is probably not going to be able to contain that pressure, so it's probably going to blow up, which is why they say with those aerosol cans, you don't want to throw them in the garbage. They still have gas in them because when they go into these incinerators, or you don't want to heat them up yourself because it can actually cause an explosion with those. Okay, and it can be dangerous. All right, it comes down to this concept, though, where pressure and temperature are related. As temperature goes up, pressure goes up. All right, let's look at another example here. I'll let you read through the specifics of it. So, what's being held constant in this case? Well, pressure and temperature are being held constant. So let's get our derived equation. Let's plug our values into our derived equation. Now, tricky part here is we have volumes, we don't have moles. All we know is the number of moles are going to be twice as much. Okay, so if that's the case, well then we just throw in 1 mole and 2 moles. And if I start with 1 mole and I get twice as much, I end up with 2 moles. Okay, it's not important exactly how many moles I have. It's important that I know that ratio between those moles. All right, now if it had given me exact number of moles, I would have put those moles in. Okay, but in this case, I just use 1 and 2, and I'm good. So I'll solve for my new volume. My new volume is going to be 3.14 liters. All right. So as I increase the number of moles, the volume of the gas goes up. So instead of memorizing all those forms, use PV equals nRT, derive the new equations, apply that PV equals nRT. That way you only have to know that one equation, PV equals nRT. Okay, we can even use this for other things about gases. For example, densities. All right, if I want to know a density of a gas, well, what's the formula for density? Density is equal to mass over volume. So let's say I take 2 moles of a carbon tetrachloride vapor at 714 torr and 125 degrees Celsius, and I want to calculate the density of that gas under those conditions. How am I going to get density? Well, I need to know a mass. I need to know a volume. Well, how do I get the mass? All I have to do is a molar mass conversion. So I know my mass is going to be 307.62 grams of carbon tetrachloride. Why? Well, because I have 2 moles of carbon tetrachloride. So 2 moles times its molar mass gives me that 307.62 grams. So what do I need to know next? Well, I need to figure out the volume. How am I going to get the volume? Well, that's using the ideal gas law, the ideal gas equation. And I can plug everything in. So I've got my pressure. Now it's in torr, I have to convert that to atmospheres. Okay, so 714 divided by the 760 will get me to atmospheres. Times V, I'm trying to determine that volume, equals, I got 2 moles of the gas, R, that 0.08206 is constant, times my temperature in Kelvin. Then I can just solve for V. I get 69.6 liters. So, I solved for my mass, I solved for my volume. Now I want to get density. Well, what do I do to get density? I take my mass divided by my volume. So my 307.62 grams divided by the 69.6 liters, and I get a density of 4.42 grams per liter. So when solving for some of these things, there's equations out there that rearrange PV equals nRT a lot and adds different things to it, and it can get a little bit confusing. Just stop and think. If I'm looking for density, I need a mass and a volume. How do I calculate mass? How do I calculate volume? Break it down, simplify it. Right? Don't try to memorize all the equations that are out there. You got to think and apply those equations to the conditions that you're looking at right now. Okay, so let's look at another example of doing this. Let's look at calculating the molar mass of a gas. So molar mass, I want to know grams over moles. Okay. So with this example problem, I'll let you read through it real quick. Okay, so with molar mass, I want to know grams over moles. So the first thing I need to do is, what's the mass of the compound? Well, I'm given that in a problem. I'm told I have 1.597 grams of the sample. So I know the mass. Now I just need to know how many moles of the compound are there. Well, how am I going to get that? Well, that comes back to the ideal gas equation. I know my pressure, I know my volume, don't know N, that's my moles. I know R, I know my temperature. Plug it all in, solve for N. I get 3.63 times 10 to the negative 2 moles. So for my molar mass, I want to know grams. I'm given that, so 1.597. I want to know my moles. I solve for that, that's the 3.63 times 10 to the negative 2. So if I want my molar mass, I just have to take my mass of the compound divided by the moles of the compound, and that'll give me my molar mass. So I end up with a molar mass of 43.99 grams per mole. So I know I have a molar mass of 43.99 grams per mole. That's going to tell me which of these gases is going to be leaking from that industrial plant. So which one is it going to be? Well, it's going to be the one that has the molar mass close to the 43.99, which is going to be the CO2. Okay, so that's how we determine that it's CO2 gas. So as far as precautions for this, we don't really have to worry about any explosion or burning hazard from CO2. We do have to worry about, though, suffocation, because CO2, if you fill a room full of CO2, it can remove the oxygen from the air. All right, let's look at another concept that's going to be important when dealing with gases. It's going to be dealing with gas mixtures in something called partial pressures. So with gas mixtures and partial pressures, there's going to be an important law. So we're going to have to deal with something called Dalton's law. Now, Dalton's law states that the total pressure of a gas mixture, P sub T, is going to be equal to all of the pressures of the individual gases added up. Now, assumptions that go along with Dalton's law, we're going to assume that the gases are going to act independently from each other. In other words, they're not going to interact with each other, they're not going to bounce off each other. They're going to act as kind of like their own individual gases. And we're going to assume that the gases don't react with each other. If you mix two gases and they react, obviously we don't have a mixture anymore, we have a chemical reaction. Okay. A real common example of this, if we take dry air, the air we breathe, it's 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide. So if you look at the atmospheric pressure right now, that pressure is going to be made up of the pressure of the nitrogen gas plus the pressure of the oxygen gas plus the pressure of the argon gas plus the pressure of the CO2 gas. Now, if we consider other things in there, if it wasn't dry air, we'd have pressure of water vapor as well. Okay, we'd have probably some other pressures from other gases in there. Okay, but all of those pressures of all those gases added together is what makes up the total pressure. So when dealing with Dalton's law, we know each gas is going to obey the ideal gas equation. So if we wanted to know total pressure, we could just calculate pressure for each individual gas. So P1 is equal to N1 RT1 over V1. Right, we can do that with the second gas. We can do that with the third gas. There's a fourth, fifth, sixth, however many gases we have, we can do it with. So now what we can look at is we can take all those different pressures, add them together, so we can create this kind of combined equation applying all those. So the total pressure is equal to N1 RT1 over V1 plus N2 RT2 over V2 plus N3 RT3 over V3. Okay, those are those pressures that we were calculating for. Okay, now when looking at this though, we can actually combine these a little bit more in that if these are all gases in the same mixture, they're under the same conditions. So what's the only difference that could be between them? Well, temperature has to be the same if they're all in the same flask, let's say. Temperature of that flask can't be varying between different gases. No, all the gases have the same temperature. That flask is going to have a very specific volume. If all the gases are inside that one flask, they all have the same volume. So R is always constant, T would be constant, V would be constant. So the only thing that's changing is those moles. So we could just pull the equation out and say the total pressure is equal to all the moles of the gases added together times RT over V. Right? That's going to lead us into something called mole fraction, where we can calculate mole fractions of a gas. So particular moles of a gas divided by the total number of moles will give us a fraction. That fraction times the total pressure will tell us the pressure of that individual gas. Right? Another thing that goes along with this is when we collect gases over water, we're going to have to apply this Dalton's law. So the total pressure of a gas collected over water is going to be equal to the pressure of the gas plus the pressure of the water. Okay, let's look at a picture of this. So let's say I have a chemical reaction going on where I have zinc and hydrochloric acid. It's producing hydrogen gas. I'm collecting that hydrogen gas in some sort of container. So as the hydrogen gas bubbles into this container and displaces water, we're going to collect that hydrogen gas. But now, that water itself is going to have its own pressure. Water is always going to form a little bit of water vapor. One way that we know this is if you leave a glass of water sitting out and you let it sit for a while, eventually that water will disappear. Why? Well, because there's always a little bit of that water going into the gas phase. Well, if it's not a sealed container, as that water goes in the gas phase, it escapes, and then more water can go into the gas phase and escape. And that process continues over and over and over again, even though we're not at the boiling point of water. Okay, same thing here. We have that water. We're going to have a little bit of water vapor in there as well. So we need to take that into account because the pressure we measure inside that container is going to be the pressure of, in this case, the hydrogen gas plus the pressure of the water vapor. The way we determine the pressure of the water vapor, though, we just get it from a table where people have done different pressure and temperature measurements. Okay, so depending upon the temperature of the water we're collecting over determines what the pressure of the water would be. All right, so let's run through a calculation that deals with Dalton's law. So I'll give you a second to read this problem. So when looking at Dalton's law, we have total pressure is equal to pressure of one gas plus pressure of the second gas. I only have two gases in this case. So I know my total pressure is 30 atmospheres. I know my pressure of my N2 is 15 atmospheres, and I want to know the pressure of my O2. Well, according to Dalton's law, pressure of my O2 gas would be 15 atmospheres. So once I know my pressure, if I'm looking for grams of O2, well, now I need to use my ideal gas equation. So taking my ideal gas equation, plugging in the values, I can solve for N, which is 3.07 moles of the O2 gas. Well, if I want to convert moles to grams, I just use molar mass, and when I do that, I end up with a mass of 98.24 grams of O2. All right, let's look at another example of gas mixtures. So with this, I want to calculate the partial pressures of each gas and the total pressure of the mixture. Well, for the partial pressure of each gas, each one I can take its number of moles times R times the temperature divided by the volume. That'll give me each individual gas's pressure. once I know each individual gas's pressure, the total pressure is just all three pressures added together.